Never be afraid. There's nothing which is known which can't be understood. And there's nothing which is understood which can't be explained. For over 50 episodes now, my team and I have brought you to the very frontier of knowledge in physics and astronomy. And still, our mission goes on. To present you with your birthright, an understanding of the universe. I've traveled the world seeking out a certain type of genius. Masters of not only their academic disciplines, but also at explaining their research in understandable ways. And I've bestowed upon these women and men the title of Titanium Physicist. You're listening to the Titanium Physicist podcast, and I'm Ben Tippett. And now, allez, physique! It's around Christmas time right now, in the end parts of December. Yesterday was the winter solstice, and the night was as long and dark as it's ever been. One of my favorite things about the Christmas season in my country is that people decorate the outside of their houses with blinking colored lights. The winter night is dark and cold and deep enough to swallow anything, and the snow packs down on the hard ground, and it's not a welcoming place. But people have their Christmas lights up, hundreds of little colored bulbs shining bravely. The warm glow reflects on the snow, and the cold air carries the light as far as it'll go, and these long, deep nights are no longer as unforgiving. As far as you can see, as far as the town and city goes, the decorated houses beam out their welcoming colors like a birthday cake lined with candles. You still might be cold, but you don't feel cold. And above them all, the cold air lets the light of the stars shine through. In the deepest part of winter, the stars are at their prettiest. And when some people think about going into space, they can only imagine how cold it is, how lonely. But because of these festive lights on nights like these, all I can imagine is how glorious the stars must look up there. You know, there are stars that blink. Like Christmas lights, they fade on and off. This surely would be heretical news to those ancient philosophers who imagined that the heavenly firmament was unchanging and static, but it's nonetheless true. It's more than true, in fact. These blinking stars, called Cepheid Variables stars, are the ladder that astronomers have used not just to discover our place in the galaxy, but the distances to other galaxies, and even explore the expansion of the universe. Okay, so Lucy Knisley is one of my favorite comic artists. She makes comic books, and she's a New York Times bestseller. She went to France and logged her experiences in a travel journal called French Milk, and her book Relish, My Life in the Kitchen, was released in 2013, and it's about food. And she just put out another book that I haven't read yet called Age of License, because my wife has hidden it from me, but she just dragged it out and showed me that we actually have a copy. I'm really excited to read it after we record the show. So listen, Lucy's books are great. They're unblinkingly honest, but they stimulate your appetite for both food and life, and I'm super excited to welcome her to the show today. Welcome, Lucy Knisley.
Thank you so much.
All right. So, Lucy, for you today, I've assembled two of my favorite titanium physicists. Arise, Dr. Vicky Scowcroft. Dr. Vicky got her PhD from Liverpool John Moores in the UK. She's currently a postdoc at Carnegie Observatories, where she works on the Carnegie Hubble program. And she also has a knitting podcast called One Starry Knit, so we'll have our link to it on our website if you want to find it. Now arise, Dr. David Tsang. Oh, a little scratchy there. Dr. David did his undergraduate at UBC with me and his PhD at Cornell. He's currently a postdoc at McGill and Caltech, researching black holes and the neutron stars and planets. All right, everybody, it's time to start talking about Cepheid variables. All right, so where should we start? They're blinking stars. How do we see them?
Okay, whether you know it or not, everyone has seen a Cepheid. The North Star which everyone knows. Like, if you look in the sky and you look at, like, the Big Dipper, the constellation that everyone knows, and it points to the North Star. Unless I'm talking to you in the Southern Hemisphere, then you might not have seen it. But, yeah, the North Star is a Cepheid.
Polaris?
Yeah, Polaris is a Cepheid. So it wasn't the first Cepheid to be discovered, but it is one of our most well-known ones. So the way they were discovered is, like, we look at them just, like, constantly for, like, days at a time. And people, like, stare at them with telescopes and see how their brightness changes compared to the other stars that are close to them. So in 1780-something in England, there was this man called John Goodricke. And him and his mate, Edward Pigott, had been, like, looking at some stars. And they were looking to see if there were any of these variable stars, which varied over time. And they discovered the first Cepheid. And this man, John Goodricke, it's really sad because he was like, Cepheids are awesome, and I'm going to look at them. So he was looking at these Cepheids. They discovered one, and then they found another one. And this is like the middle of winter in England. And I grew up there, so I can tell you it's horrible. It's cold, and it's wet, and it's rainy. And so he was in Yorkshire. And he discovered this Cepheid, and he's like, I want to work out how fast this star changes brightness. So every night he went out there and he looked at this Cepheid and, like, compared its brightness to the other stars and, like, mapped out how the star changed. And he was out there every night for months. And he became so obsessed with this star that he caught pneumonia and died from Cepheids. That was the end of John Goodricke. But basically, that's what we still do today. So we look at these stars typically from a few days to a few months, and we measure how bright they are, and we look for the ones that change. And, like, if they change by a certain amount, then we say that one's a Cepheid, and that's how we find them. Does that make sense?
Yes.
You don't die now. I am yet.
Right. Now there's technology, like being inside. How did they, like, measure the brightness in comparison to the other stars, though?
So in the 1700s, like, this guy basically just looking by eye. And he's like, well, this one looks brighter than the one next to it today. And it looks fainter than that one next to it. And he just drew a map. But today, what I do is I use a telescope. I use a telescope in space called Spitzer. But we can do it with the Hubble Space Telescope as well. And we have basically a digital camera on it. Exactly the same as the one in your phone. Actually, the one in your phone is probably better because ours were made, like, 10 years ago. And they had to be, like, really well tested to go into space. So the ones in your phone are much more advanced. But we take a picture of them, and the ones around them won't change. Like, the other stars won't change. So we can calibrate. We can say, well, we know these ones aren't changing. But then the ones that are changing, we can see how they're changing over time.
How long do the changes last?
So it's quite like a regular change, like a sine wave. Do you know what that is?
Mm-hmm.
Okay, so they look like a sine wave, basically, and they take typically 3 days to around 60 days, but it carries on like that for, like, hundreds to thousands of years.
It just seems really incredible that people could use their eyes to tell that pulse. Like, as a 60-day pulse, like...
The one that he measured, like, that killed him was, like, 5 days. And he measured it so well, he got it, like, almost exactly to what we measure it to today.
Yeah, people's eyes are pretty good at gauging intensity of stars, right?
Yeah.
So it's about relative intensity. So he compared it to stars that he knew the magnitude of. That's the sort of unit we use, magnitude of stars. It's a logarithmic unit, but so if he knew this particular star was, what's the standard star? That's
Vega.
Vega, and what's its magnitude?
0.
0, okay. So you compare it to Vega, and that has a particular brightness, which we call magnitude 0. And then you might compare it to other stars where people have sort of figured out, okay, this is the particular brightness of this star. So because we're good at doing relative brightness, they were able to sort of pin it down that way.
Yeah, your eyes are very good at telling whether something is brighter or fainter.
But yeah, it was still a very difficult task.
Yeah, it was still really hard, and, like, there was only a couple of people that could do it.
Can you imagine going out in a telescope and being like, I think it's 4 tonight?
I know, yeah, it's crazy. I'm glad I don't have to do that. I'd get cold.
Yeah.
So yeah, that's how they were discovered.
Cool.
So they're useful because we can measure their periods. And it turns out that a very famous astronomer discovered that there's a relationship between how large the brightness change is to how long it takes for that brightness change to occur. Because
not quite.
Oh, no? Okay.
No.
You go ahead.
So this woman called Henrietta Leavitt, she's awesome. She was like what they called a computer at Harvard, which I think is stupid. They should just call her an astronomer, because she was. But because she was a woman, they were like, no, you're just a computer. You're not a real astronomer, lady astronomer. So her job was basically to do a catalogue of all these stars in one of our nearest galaxies. So she looked at all these stars. I'm not sure they even knew it was a galaxy at that point. They were just like, look at all these stars over there. And she looked at them all, and she found that there was a relationship between how fast the brightness changed, between like the period of the brightness change, and how bright the average brightness was. So if you took the average of the brightness and the period, she found it like a direct relationship. And because of that, like if you knew the period and you knew how bright the star looked to you, you could work out how far away the star was. For example, if you had like a 50-watt light bulb and you held it up to your face, it would be like super bright. But if you had it on the other side of the room, it would be less bright, but it would still be a 50-watt light bulb. And you could work out how far away that light bulb was by working out how bright it should be and how bright it actually looked to you. And she was basically doing the same thing with stars. And she was the person that discovered this. So she worked out that we could work out the distances to things by looking at how fast the brightness changes were in these stars. But like she never got any credit for what she got some credit for it at the time, but basically because she was a woman, she didn't get the proper credit for it. So they were just like, yeah, poor lady astronomer. But now, like I think it was like 5 years ago, the International Astronomy Union, which is like in charge of like all the astronomers in the world, basically passed this astronomy law that we have to refer to this relationship as the Leavitt law to like give her the proper credit.
Nice.
So that's good, yes.
There's a long history of male astronomy professors taking credit for the discoveries by women astronomers that were employed by them.
What was the concept of the computer title at Harvard? Were there male computers or were they all women?
I think they were all women, basically. So, like, this was in the 1920s, and there'd be, like, one professor, and then he would have this collection of women computers who would do all the calculations and do all the observations and basically do all the hard work.
As I half remember it, the deal is that modern computers take their title from this job that you could get, where you could essentially do repetitive tasks over and over, like comparing stars or adding long tables of numbers. And so it's a job you could get essentially just doing a repetitive task. And they found, this was like Victorian area, that, you know, you'd employ a warehouse of computers to add up numbers together or do a calculation for you. And they found that women were better at it than men. They were like, men get distracted and make lots of mistakes, but women never make mistakes, and their eyes are really keen.
Like getting pneumonia and dying.
Yeah, that's right. So it's probably just the title of computer is a laboratory technician type thing at Harvard probably is inherited from this previous job. And the deal is that modern computers have just taken over that role. So a computer can take a photograph and compare things for you, or a computer can add long chains of number for you instead of having to employ a warehouse full of people.
Yeah, but she was awesome. And like she discovered all this stuff, and the relationship that she discovered is like basically exactly the same thing we're using today to work out the distances to all the other galaxies in our local neighborhood. Like, it's exactly the same thing I use right now to measure the distances to other galaxies and to like, work out how fast the universe is expanding. It's not like this old thing that's like, oh, well, she discovered this thing that we used 100 years ago. This is like this thing we still use to like do cutting edge astronomy. It's cool. Like, it's super cool. I think it's cool anyway.
So the thing that Vicky was referring to is a type of technique referred to as a standard candle. That's what she was saying with a 50-watt light bulb, right? Because a 50-watt light bulb, it doesn't matter which socket in the house you plug it into, it will shine with the same intensity. So if you know a light bulb is 50 watts, if you knew that beforehand, you can use the brightness you observe based on where you're standing, and then the knowledge that it's a 50-watt light bulb to figure out the distance. So in these standard candles, you measure the amount of time it takes to go from bright to dim to bright to dim. And then you look it up and you say, okay, we know how intense the light is coming off it. We know how bright it is. And so it looks pretty dim to us from here, so it must be really, really far away. And so you can calculate numerically how far away it is based on knowing how bright it is as we measure it.
Because the dimness is the star further away from us, is that correct?
Yeah, light's kind of like sound. The farther away somebody who is speaking is from you, the less intense the sound wave is, or the less intense the light wave is. So, in essence, these standard candles, so these Cepheids, the farther it is away from us, the dimmer the light will appear. So if it's 5 galaxies over, really, really far away, it'll be really dim. Even if it's one of these stars that shines a ton of light out, it will still look dim. But because we know how much light it shines out based on its period, we can figure out how far away it is from us by figuring out how intense it looks from our perspective.
Okay.
The key is that the period that we measure doesn't suffer from any bad effects from being far away. So that from that timing, we can ask Henrietta Leavitt and use her law to tell us how bright it should appear to us. And then from that, we can figure out how far away it is from how bright it actually looks to us.
How bright is the North Star? Like, is it one of these ones that blinks out entirely, or?
Just a short period, like a few days, so I think it's pretty faint. The North Star is really weird. Like, it's evolving right now, so its period is actually changing, and it's almost not pulsating anymore. There's something weird going on with it. I haven't looked at this for a while, but it's almost not pulsating anymore. So, like, this is another weird thing about Cepheids. Like, so they start off as a different type of star. Basically all stars start off as the same type of star, just a regular star. And then some of them, as they age, the conditions are right and they turn into Cepheids. But eventually they become a different type of star again. And the North Star is in that stage where it's becoming no longer a Cepheid. And it's moving away from the Cepheid stage. So we can actually see that happening, like, on human timescales. So as we repeatedly take more images of it, we can see that the brightness changes are starting to disappear. So
nobody knows why that's happening?
We know that it's to do with the evolution and it's changing into a different type of star. The good thing about the North Star is that it's within our own galaxy and we have a lot of observations of it. So we don't always get to study a star like this in such great detail. So we don't always have a lot of examples of this. So this is like one of our first opportunities to study it in really amazing detail.
We know generally why it's happening. It's leaving a stage of its evolution called the instability strip.
Yeah.
Instability here refers to the fact that it's pulsating.
Right.
Yeah, so it's becoming a stable star again. And we have, like, a general idea. We have models of, like, what is happening to stars in that situation. But, like, this is one of the first chances we have to, like, really make an in-depth study of this. So it's really exciting, actually, that we can look at that. So we have an idea, but I don't have a huge idea because it's not my specialist thing.
But we do know the mechanism that causes Cepheid variables to pulse the way they do.
We do.
Yeah, we're just not sure about the details as to why the North Pole star is doing what it's currently doing. But we know why, nice stable Cepheids that are pulsing pulse.
We do, and Dave will tell you about that when he stopped coughing.
Yeah. Why don't you start, Ben?
Okay, sure. Let's talk about what makes up a star. The deal is that it was a big cloud of gas that collapsed down in on itself. And so now it's a sphere of gas and plasma. And at the center of this sphere, nuclear fusion is taking place. And that's releasing a ton of energy. So on the inside of a star, like our sun, we're burning hydrogen into helium. And that's releasing a whole bunch of energy. So the inside is really, really hot. So that generates a whole bunch of light that pushes outwards and tries to leave the sun. And that's the photons that we see bathing us every time we go out. Now, the deal with Cepheids is it kind of has to do with chemistry of the outer layers of gas and how opaque they are. The deal is that in these stars, the outside of the ball of gas is kind of opaque. It's not letting very much light out. Not as much as it wants to. And so energy is building up and building up and building up inside of it. And this causes the star to puff up. It gets bigger. The outer envelopes, the part we can see, get really, really, really hot. and they get so hot that they change the chemistry of the outer envelopes and it becomes transparent. And then as soon as it becomes transparent, all those photons explode out and the star gets really, really bright. But then doing so lets the temperature inside drop, and then the star shrinks down and the chemistry goes back to what it once was and it becomes opaque again, and energy starts to build back up.
So imagine a pressure cooker that was made out of a balloon.
It sounds horrible.
Yeah, it is terrible. So now we have a valve in this pressure cooker that lets stuff out. But let's say I broke the valve, and as the temperature increases, it lets less stuff out.
Mm-hmm.
As the fusion goes in the star, inside the pressure cooker here, the temperature goes up, and that makes the valve release even less of the pressure. So that will cause the balloon to expand until the pressure falls enough that you match what comes out. And then it lets the pressure go because the temperature has gone down because the balloon's expanded, and then it can shrink back down again. So that's kind of what's happening in the star. Because the amount of light it lets through, or the amount of pressure it releases, decreases as the temperature goes up. The star itself expands like the balloon does until the temperature goes down enough that it can let the light out. And then it shrinks back down again. And that's what causes this cycle.
So the moral of the story is that this star, it's not letting energy out fast enough. So the energy's building up inside of it. And then what happens is it gets so hot that it just kind of melts the outside and all the energy can escape. And the star gets really, really bright. But then it's letting the energy escape faster than it's being generated, so it cools down and shrinks down until the initial conditions restate themselves and it becomes opaque again, and then it will start puffing back up.
Yes, except for the fact that larger stars appear brighter to us, correct?
Right.
So if it's puffing up, wouldn't it then appear brighter to us if it's puffing up?
But because the atmosphere is opaque, none of the light can escape.
Okay.
So all the light is trapped inside it. So the bigger ones normally appear brighter, but this is a special case because all the light's trapped inside. So when the light does escape, it appears brighter because it's bigger.
It appears like really, really, really bright.
Yeah.
Because all that trapped light is escaping.
Yeah,
Right.
It's just, as it's getting bigger, all that light is trapped.
Is the growth observable?
Yeah. Yeah, we can measure it. There's this huge telescope in Chile called the Very Large Telescope, because astronomers are super original.
Not to be confused with the Extremely Large Telescope.
Or the now defunct Overwhelmingly Large Telescope.
Oh no, it's defunct.
I know, I was so looking forward to the owl. But they have this special setup, basically, where you use lots of telescopes together, and you can measure, we can literally measure the width of these stars as they grow, and we can see them growing.
Do they change in brightness as they grow?
Yeah, you can see them change in brightness slightly, but you can actually measure the physical size of them change.
Oh, neat.
Yeah, it's really cool.
So the difference between this and a normal star really is sort of that pressure valve, whether how much light it lets through as a function of temperature. So normal stars, as you increase the temperature, you tend to let more light through. But in these stars, in the stage of their evolution and the chemistry that's involved in that stage of the evolution, as the temperature goes up, less light gets through.
Yeah, there's a lag.
That's why these guys pulsate like this. Stars in sort of the regular portion of their lives don't tend to pulsate.
Is that because they lack this outer layer of gases?
They have different chemistry in their outer layers, I guess.
Yeah, this one has a layer of helium with a special ionization state. So it's got a couple of the electrons have been knocked off the helium in the outer layer. And regular stars, what we call main sequence stars, which is what most stars start off as, you're just burning hydrogen. But these ones are a much later in the star's lifetime. So all the hydrogen's gone and now we're going into helium. So this is a much different type of star.
It's a different flavor.
Yes,
Yeah.
basically.
Okay.
It's an older star.
Yeah.
Stars can change a lot over their lifetime.
Oh, okay.
You want to talk about the history of how we use them to expand our idea of what the universe is?
Okay. So Hubble, who the telescope is named after, he used to work in my office.
What? Your actual office?
Well, not my actual office, not the physical
His
office.
office is upstairs.
Yeah, he's upstairs.
Okay, so he worked in the same building as you. That's still impressive.
Yeah, he was at Carnegie.
Cool.
So was Einstein and all the cool people. Anyway, so Hubble One of the things he studied was Cepheids.
There was a time when we thought that our galaxy was all there was to the universe.
Yeah.
And that all of the other things that we recognize now as galaxies only looked like smudges. So we thought that they were just clouds of gas out past the edge of the universe, our galaxy.
So yeah, Hubble, while he was in my office hanging out, he was looking at a nebula called Andromeda, and he found some Cepheids. And by looking at these Cepheids, he worked out that Andromeda must actually be a really long way away. It couldn't be part of our own galaxy. So it must be like really far away. And that's how we found out that actually our galaxy isn't the only thing there is. There must be other galaxies outside of our own. So yeah, basically that was the discovery that we are not the only thing in the universe. There are other galaxies outside our own. And that was just from looking at Cepheids. And it's really cool. You find these pictures like that he'd taken on the telescope in, I think it was on Mount Wilson, which is in Los Angeles. We still have these photographs that he took, and he's basically drawn on them. It just says variable ! Where he's found these Cepheids. And he's worked out that this galaxy is a real thing. It's not just a cloud. So then, like, maybe 15 years later, he'd continued to do this, and, like, he'd found other galaxies. And then what he'd worked out is that each of these galaxies that he'd worked out the distance to were actually moving away from us. So he'd calculated how each of these galaxies was moving away from us, and he'd worked out their distance. And he'd found that there was a relationship between how fast they were moving away from us and how far away they were. And he'd found that the ones that were further away were moving away faster. So basically, we were in the middle and everything was moving away. But like the further away it was, the faster it was moving away. Which basically was evidence that we were in some kind of explosion. And that was like the first evidence that we had expanded into the universe that we know we're in now. And again, this is all from like just these few Cepheids that had been discovered in different galaxies.
So let's take a brief tangent away from this. So he was doing this in context of Albert Einstein and other people working on Albert Einstein's theory of gravity. So Einstein's theory of gravity, if you make some very simple assumptions, it lets you describe what the universe looked like. And Einstein and the other people working with Einstein's theory imagined that the universe, there's something called the Copernican principle. Do you remember who Copernicus was, Lucy?
Yep.
So Copernicus was the guy who said that the sun doesn't go around the earth, right?
Right.
Copernicus is famous in European history as being the person who said, hey, the earth isn't the center of the universe. And so we extend his theory as saying, as we say, okay, so the earth isn't the center of the universe, and neither is the galaxy, our galaxy, the Milky Way, the center of the universe. There must be other stuff farther out, equivalent to our own. So the Copernican principle says that there's nowhere in the universe that's any different than anywhere else in the universe. So if I were to go 100 jabillion parsecs away in that direction, the universe would look pretty much the same as it does here, give or take. You have to do some averaging. You have to say things like, well, you know, the average mass density of the universe over there is going to be the same as over here. The average temperature over there is going to be the same as over here. And that assumption has been borne out in observations that came later in the 60s. But so back this truck up, Einstein was saying, here, we've got a theory of the universe that we can use, a theory of how the universe looks at very large scales. The problem with his theories, though, is they predict a dynamic universe. So in his model of the universe, what you imagine is that the universe is infinitely large and infinitely wide and infinitely tall, and that the mass density and the temperature at every point in the universe is the same, but the universe will expand over time, and as it expands, things cool, the matter becomes less dense. And the problem with this assumption is that Einstein, he hated this conclusion that his theory naturally drew that the universe was dynamic. He wanted the universe to be static, something that never changed. Because, you know, up until Hubble came along, there was no reason to think that the universe would change for any reason. We imagined that, you know, the stars would always be in the sky somewhere. I guess they would go out in some places, but other stars would be born. And that the universe would, you know, on average stay the same over all time. And so Einstein, famously, he calls it his biggest blunder. He inserted a term into his equations called the cosmological constant, which let him build a model of a universe that never changed over time, that wasn't dynamic. And so he was happy with that, and then immediately after publishing that, Hubble published his groundbreaking discovery that the universe was indeed expanding, which is crazy because it confirms the prediction that his theory predicted that he tried to change his theory to get away from. So, boo to that. There's a fun history of that. Moral of the story is, it turns out that at very large scales, the universe is increasing in size. Einstein's theory describes the idea of distance as being a dynamic quantity. I'm not sure how to put this in a way that doesn't involve me giving you a lecture on general relativity at this point. We're trying to keep it to kind of Cepheid variables. But the idea is that it's not that other galaxies are moving farther away from us. It's not that our galaxy was the center of an explosion that pushed all these galaxies away from us. But rather, the distance between us and farther galaxies is dynamic.
It's like a cake. If you baked a cake with raisins in, and like initially all your raisins would be close together, and then as you baked the cake, all the raisins would get further apart because the cake itself would be expanding, because the space between the raisins would be getting bigger, because the cake would be expanding.
For any given raisin, it would look at all the other raisins, and it would notice that the raisins that are further away from it are moving away from it faster.
Yeah. Even though any raisin wouldn't be at the center of the cake.
So every raisin would look at all the other raisins and say, I'm the center of the explosion. All the other raisins are moving away from me.
Right.
So that's essentially what Hubble discovered, is that the universe is full of other galaxies. Those galaxies look like they're moving away from us. But the details of the way they're moving away from us mean that it doesn't matter which galaxy you're sitting in. So you put your astronomer down in any galaxy in the universe, they'll look at up all the other galaxies expanding away from it and say, oh, our galaxy is the center of the explosion. Because there is no center of the explosion. It's this distance between the galaxies that's increasing. And so the larger the distance is, the faster the rate of increase.
Okay, yep.
So the deal is that we want to get a better understanding of how the universe is expanding. We know that it does, thanks to Hubble and thanks to Einstein's theory, but we still want to work out the details of it. For instance, have you ever heard of dark energy?
No.
Okay. Well, there's a couple kind of gaping holes in our theory of gravity. In essence, when we model how gravity should make, galaxies spin, or how Einstein's theory of gravity allows the universe to expand, there's a couple types of matter that we're not seeing observationally. So one of them is called dark matter.
Right.
It's a type of matter that doesn't interact with light. And so we can't see it, but it looks like it's clumping around the centers of galaxies, and it lets the galaxies spin faster than we would otherwise expect, just counting the stars. So the galaxies have a lot more mass than we'd expect. But there's another type of it's called dark energy, and it's causing the universe to accelerate in its expansion. So the deal is that in the model for the universe expanding, what Einstein's original theory predicted is that the universe would expand, it get bigger, 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 and then maybe recollapse on itself. You might have heard of that. Mm-hmm. But what we know, and we've known for marching towards 20 years now, is that the universe isn't going to recollapse ever. It's expanding at a faster and faster rate. So over time, the universe is accelerating. This dynamic distance between us and faraway galaxies is increasing. So the speed at which the universe is getting bigger is increasing. It's getting faster and faster and faster, and we're not sure why. We say mathematically that the cause of that is some type of matter that we've never detected called dark energy. Anyway, moral of the story is that we figured out that this must be true using a type of standard candle that we haven't talked about yet. So before I was telling you that this idea, there was a 50-watt light bulb, and you could tell based on how bright it was, the distance away, because you knew how much light it was putting off. So the farther away it gets, the dimmer it gets. And we use Cepheid variable stars to figure this out. There's another type of standard candle called a supernova type 1A. And what happens is, there's like a white dwarf somewhere and matter's falling in on it or something, and it explodes. A ton of energy comes out of it. It's really, 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 really bright. Brighter than a galaxy bright. But the thing is, these specific types of supernova, they get dimmer over time. After the big explosion, it gets dimmer. And we know that there's a precise relationship between how long it takes to get dim, the rate at which it's dimming, and how bright it originally was. Mm-hmm. And so we can use these as standard candles. And because they're so bright, like Cepheid variables are wonderful, but you can't see them really, 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 really far back because they're too dim. But these supernova 1As, rarer occurrences than Cepheids, but they're super bright. And so we can use them to figure out how far away really, really distant, dawn of time distant galaxies are. And the thing about that is the universe is expanding, but the rate at which the universe is expanding changes over time. I mentioned before that it's speeding up.
Right.
And the way we know it's speeding up is that the light emitted from these supernovas really, really long time ago, this light has experienced a large chunk of the history of the expansion of the universe. And so based on how far away it is, the farther away they are correspond to how long ago they were emitted. So we can look at these specific standard candle supernova and figure out how the rate of expansion has changed over time. And this is how we know that the universe is accelerating. But the problem is that there isn't all that much data on it, right? Because we counted all those supernova, and we have a good sense that the universe is expanding in one specific way. We know that the expansion is accelerating, but we don't know if, say, that acceleration is accelerating or that acceleration is decelerating. And there's all sorts of end states of the universe that can happen depending on what this dark energy is doing. So the more we know about how the universe is accelerating, the more we can figure out about this dark energy. But we don't know very much yet. All right, Vicky?
Okay, so my job is to, make sure that all of those measurements of the supernova are, as accurate as they can be. So to do that, I take all the measurements of the Cepheids. And because these supernovae are so far away, because they're very rare, it's very, very, very rare that we ever get one in a nearby galaxy. We had one last year, was it? It was last year, and it was the first time in a very, very long time we'd ever had one in a nearby galaxy that you could actually see, with your eyes, without looking through a huge telescope. And this was a huge thing that happened. But most of the time they're in really far away galaxies. So my job is to take the observations of the Cepheids in the furthest away galaxies that I can possibly do, and where we also have one supernova that's gone off, and try and match them up to make sure everything is consistent, and try and find out if there's any way that anything could have gone wrong, or try and work out what's happening, or if there's anything we haven't thought of, maybe there's some weird stars in that thing, or maybe that type of galaxy has got some weird stuff happening, or maybe there's just something weird about that type of Cepheid, or there's that galaxy has lots of dust in it or something. But that's my job, basically. Dust is a big problem, and not just in my house. But yeah, that's basically my job. But the other thing we've started to do now is try and look at other ways we can do this, because there's this big problem right now. Well, I say it's a big problem, but it's a big problem for people like me. There's this other experiment called Planck, where they found a completely new way of trying to measure how the universe is expanding. I won't go into it now, but it's completely different. They use this thing called the cosmic microwave background. It's the patterns left behind by the Big Bang, basically, but it doesn't use stars. It's completely different from what we're doing. And the answer they get from that doesn't match up with the answer we get from Cepheids and supernova, which is kind of bad. So now we're trying to think up a new way of trying to measure it.
To reconcile the two.
Yeah, because right now, we have our way, and we're well, we're fine. We didn't do anything wrong. And they have their way, and we're well, our way is fine. So now we have to try and think of a third way. Our idea for the third way is we've got this other type of variable stars called Aura Lyrae, which are similar to Cepheids, but they are really, really old. They are the oldest stars in the universe. So the universe is 13 billion years old, and so are Aura Lyraes. They are the first stars that formed in the universe.
Second stars.
Yeah, the second stars that formed in the universe. Sorry, Dave. But they are so old that they basically have, like, newer stars have, like, contamination from like, when supernova went off, they released all their crap into the sky and all that stuff. But these stars are so old, they don't have any of that. They're really interesting because they're like that. So we're going to try and use those instead to try and fix this problem.
So there's a lot of comparing different ways. You need overlapping ways of measuring distances. For instance, to measure the distance to these supernovae, you have to have them overlap with where you can see Cepheids. So you need to have them in the same galaxy. And in order to calibrate our understanding of Cepheids, to figure out that distance relation, we need some Cepheids that are close enough so that we can do what's called parallax on them.
And parallax is like, so if you close one eye and then close the other eye and you see that the things that you can see move,
right?
That's basically parallax.
Right, because that's a combination of the distance from you to that object and the distance between your eyes.
Right.
Yeah.
And so we can do the same thing, but for different sides of the Earth's orbit.
Cool.
Yeah, so that's how we, like, measure the absolute distance to a star.
But in order for us to figure out what the parallax is, we need to know what the size of the Earth's orbit is. So that involves us figuring out what the distance is to the Sun, which comes from, I think, radio ranges to Venus. But it all comes back down to laboratory measurements of the speed of light, because that's how fast radio waves go.
Okay, yep.
So it all starts from, like, figuring out how fast light goes, and then we gradually step up and have all these overlapping measurements until we can figure out how far apart these really, really far away galaxies are.
Cool.
Well, that was fantastic. Thank you, Vicky. Thank you, Dave. You've pleased me. Your efforts have borne fruit, and that fruit is sweet. Here's some fruit. Dave, you get a mandarin orange, the most variable of oranges. And Vicky, you get a Terry chocolate orange, because high-quality work today. I'd like to thank my guest, Lucy Knisley. Her latest book is called An Age of License, a Travelogue. It's lots of fun. Thank you, Lucy.
My pleasure.
I hope you had lots of fun. All right, hi, everyone. Okay, so it's announcement time. First, I hope you've enjoyed the Question Barn episodes. If you'd like us to answer your questions, send your questies to TIPHYTR at titaniumphysics.com. TIE Fighter at titaniumphysics.com. Good. Second, good news, everyone. Our Patreon campaign has reached $100. That's our second level of funding. So we're going to start, we're going to use that money to get 2 episodes, a current episode and 1 past episode transcribed. Our transcriber is working as fast as he can, but he's a physics student, so he doesn't have the most time in the world. I'm going to start putting them up as PDFs at the bottom of the current and past episodes as he does them, and so they should be searchable by Google. I'm really excited. Okay, so on that note, I'd like to remind you that we're now accepting your donations. We'd be grateful to receive your support. You can make a one-time donation via PayPal through our website, or you can set up an automatic donations each time I finish an episode through our Patreon website. This particular episode of the Titanium Physics podcast has been sponsored by a collection of generous people. I'd like to thank the generosity of a man named Hugo for his support, and also a Mr. Ryan N., a Mr. Adam K., Thomas Sherry, and Mr. Jacob S., a gentleman named Brent Evans, a lady named Jill, a gentleman named Greg. Thanks, Josh and Steve, Mr. James Clausen, Mr. Devin North, a gentleman named Scott, Mr. Ed Lowlington, Kelly Wienersmith, Jocelyn Reed, Mr. S. Hatcher, Rob Abrazado, and Mr. Robert Stietka. Thanks also to Brent Knopp for remastering our intro. I appreciate all of the help on my poor audio skills. So that's it for Titanium Physicists this time. Remember that if you like listening to scientists talk about science in their own words, there are lots of other lovely shows on the Braculo Media Network for you to listen to. Remember, there's more podcasts out there than the Serial Podcast. Okay, so the intro to our show is by Ted Leo and the Pharmacist, and the end song is by John Vanderslice. Until next time, my friends, have fun, and remember to keep science in your hearts.
Angela, don't be mad. There's something I gotta tell you, dear, before you come back here. I lost your bunny. a cage. He was eating spring mix on the carpet. Jumped through a window out into the haze. Hop down Magnolia Boulevard. No way he'll survive.
Or imagine you have a dough of bread. Like, imagine you wanted to be a bread maker, but you weren't very good at it, and you put way too much yeast in it at first, and you also decided to videotape it instead of baking it. Okay? So you have this ball of dough, right? And inside there's yeast. And the yeast, I mean, the hotter the yeast gets, the more it reacts. But, you know, all these yeasts, it's producing carbon dioxide, right? It's producing air, right?
Mm-hmm.
Okay. Now, because you made you kneaded the hell out of the bread's not letting any of this air escape. Okay? And so it puffs up. It increases inside, right? Bigger,
Yep.
bigger, 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 bigger. It's inflating. Because it's not letting any of the air escape. Just like in these stars, because the outer envelopes are opaque, they're not letting any of the energy escape. Okay? So it's puffing up and getting hotter and bigger until in the bread dough, what'll happen is the bread dough isn't strong enough to contain all the gas anymore, right? And so maybe there's a bubble and it ruptures, and then your bread dough will go. And maybe a souffle is a better example, and it shrinks down and gets small again, and then the bread dough will heal itself and become a nice, it can contain itself again. And then it'll start the process over again, inflating, deflating. I don't know, does bread actually do that?
No.
Oh.
Well, it'll overprove and the yeast won't grow anymore.
Oh, don't grow anymore. I don't know. I've only gotten to the point
Maybe
where...
get 2 or 3 rises out of it, Ben.
What's that?
Yeah. I mean, it'll rise again. But
Yeah.
there's a limit on the rising.
Like
Sure.
itself.
Yeah, but you're supposed to knead it between rising again, so you're actually pushing it in. I'm not sure if that's the greatest metaphor. I just like bread. But it usually tastes gross after you let it do that too long. Anyway,